What's up, people? How's it going? Welcome back to CSES, Sundar. So, this video is exclusively for segment trees. Here, I will be talking about what segment trees are, why people go for segment trees, and how powerful segment trees are. So the real motivation comes when we want to solve range-based query problems. Now let's say this is the problem that I want to solve with segment trees, right? So we'll be given an array and we'll be having Q queries. And in all the Q queries, we want to find out the minimum value, right? So this is one of the problems. And the other problems are like we'll be asked to update some of the values inside some range and perform some queries. So whenever we want to update some values in a particular range, and also answer some queries regarding some ranges, we'll be going for segment trees. Now, let's say we have an array A which has its elements as 2, 3, 5, 7, 4, and 5. I'm asking you to find the sum of the values in the range of 2, comma 3 or 2, comma 4. So the sum of the values in this range will be 15. Right? Now, let's say I want to update the values in the range of 2, comma 4, and I want to increment all the values by 2, right? So if I want to increment all the values in the range of 2, comma 4 by 2, then usually what you'll be doing is you'll be trying to form a loop, and then you'll be going to all these indices and you'll be implementing it, right? So this particular array will be converted to, right? So this will be the new array which we'll be dealing with for the further queries. Now if they ask to find out the sum of the elements in the range of 2, comma 5, then is to be reporting the answer with 5 plus 7 plus 9 plus 4, right? Which is ultimately 25. Now, can you use prefix sum logic for this, which we discussed in the first video? No, because once we update the values, the new array will be different from the previous array. So we have to again construct or modify the prefix array. Hence, we cannot directly use prefix array logic over here. Right. Now, if you want to find out the sum in the range of 2 to 5, then you have to again construct a loop and you have to loop through these indices and you have to find out the sum. Right. Now, this runs in linear time because you have to create a loop time and again and you'll be solving for each and every query. So what if I say I can update as well as answer the queries in logarithmic time, right? So the first about segment trees is that and I can answer the queries, even update the values inside any range in logarithmic time. So the main motive for going to segment trees is the complexity behind performing the activities. Now, how to update some range and take out the sum with the use of segment trees, right? So in segment tree, we'll be following divide and conquer. Right. Now, whenever we say logarithmic time, it's mostly either binary search so, or divide and conquer rule or something related to trees. Right. So all the balancing will be having its height as log of n, if n is the number of nodes that we have. Right. Now in segment trees, we'll be constructing a binary tree which is balanced. Since the maximum height that we can go will always be log n, right? So that's why the updating and then the queries will be working in logarithmic time. Right. Now, how to construct the segment tree for the given array? Right. Now, I'll be dividing the array into two parts. So, one will be having the first half, and then second array will be having the second part or the second branch. So, the first part will be 2, comma 3, comma 5. That is the first three elements. And then the second part will be having the next three elements. That is 4, means 7, 4, and then 5. Right. Now, let's divide these two subarrays again. Right. So, I can divide this into two parts. Now, the first part will be having the elements as 2, comma 3, and the second part will be having a single element as 5. Now, if you divide the array 7, 4, and 5 into two parts, then we'll be getting. Now, let's just further divide the arrays which have more than one element. So, this is the segment tree that I can have for this particular array, right? So, what I'm doing? So, I'll be just dividing all the arrays such that the arrays are divided into near about equal parts. That is, I'll be first dividing the six elements into 3 and 3, right? Now, this three elements will be again divided into nearly equal parts. That is 2 and then 1. Right. Now, this should be done until we reach arrays of single element. Right. Now, how can we construct or how can we get the sum for these elements? Right. Now, if I just try to calculate the sum for these elements, Then for the leaf node, the sum will just be 2 because there's only one element, right? So this will be 3, this will be 2, and this particular array will be having its sum as 5, and so on. Right. Now, if you want to calculate the answer for 2 and 3, it will be nothing but it will be the sum of all the elements of its children, which is 2 and 3. So if if you try to calculate the answer for 2, comma 3, that is this particular index, then the answer will be 2 plus 3, which is 5. Right. Now let's try to calculate the answer for 7 and 4. That is this particular node. Right. For this node, the answer will be the sum of all the elements of its children, which is 7 and then 4. Hence, the sum will be 7 plus 4, that is 11. Now, if you want to try to calculate the answer for this node, which has its elements as 2, 3, and 5, then it's nothing but the elements or sum of the elements of its children, which is 5 and then 5. So here it's implementally known to us that this 5 was not a single product. So this 5 was already a sum of two of its children, right? So all we care about is the sum of its children. So for this particular node, the sum will be 5 plus 5, which is 10. Now for this node, the sum will be 11 plus 5, that is 16. Now for the root node, the sum will be the sum of its parents, which is 10 plus 16, that is 26. So this is how the segmented tree will look like when we try to visualize. But when we try to construct this particular thing, I will not be making a tree, but I'll be instead storing these values in an array. So if you know the concept of heaps, so we'll be following the algorithms of a tree, but we'll be applying those algorithms on an array. So that's the same idea which I'll be following for segment trees. So instead of explicitly creating a tree, I'll be creating an array where I'll be showing these and I'll be keeping indexes to jump between its parents and children. Let's say I give the index for the first element as 1. Now, this particular node will be having its index as 2 and followed by 3, 4, 5, and so on. Right. So this node will be having the index as 4, 5, and so on. Now here, I have assigned all the nodes an index, right? So the first root node will be having its index as 1, and then its children will be having the indexes 2 and then 3. Now, 2 is the parent node, and two's children will be having the indexes 4 and then 5. And similarly, three's children will be having 6 and 7. Now, can you spot a pattern over here? So if the root node value or root index is I, then left child will be having the indexes 2 into I plus 1, and then the right child will be having its particular index as 2 into I plus 1. Sorry, it should be I over. Right. So the roots node over here is 1, and its children will be having 2 into I and then 2 into I plus 1. That is 2 and then 3. Now, if you just see this particular node, so its index is 2, right? So its children are having 2 into 2 and then 2 into 2 plus 1. Now, similarly, 3 has its children's index as 6 and then 7, which is 3 into 2 and then 3 into 2 plus 1. Now, similarly, if you see, we don't have any children for the nodes 5, but its children should have been 10 and then 11. Only if we consider those nodes or fill those values, then we can get some continuity in the values. Because the node 6 will be having its children's value as 12 and then 13. If you notice for the node 4, the children will be 8 and 9. Right? So in continuity, the values will be 2, 3, and then it will be going to 7 and 4. So instead of that, we'll be taking some place and then we'll be filling the values 10 and then 11 so that we have some continuity in the values and some continuity in the pattern. Right? So the continuity in the pattern only exists if we mark all the levels irrespective of whether some values are present for that particular node or not. So let's say we create an array called 3, and this is the indices that I have, right? So now I'm just write down the indices in the first place, right? So we have the indices 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now if you see, what are the values that corresponds to these values? So the first index has its value as 26. So this is the indices that I have, and the tree array will look something like this. So the first index has a value as 26. That is, 26 is the sum for the first index, and first index represents the whole tree or the whole array. Now the second index has its sum as 10, followed by 16, 5, 5, and then so on. So this is what the array tree will look like. Then we fill all the values. Now, if you see some corresponding values, let's say we look out for the index of 6, then the 6 index will be having the sum as 11. And 6 index represents this subtree that we have. Right? So this subtree sum will be 11. So that's what this tree array indicates. Now, let's just check out the values of 10 and 11. So for 10 and 11, we don't have any values, right? So these values or these values in the tree will be filled with some garbage values, right? So that's all about it. Now, if you want to put out the steps to construct this tree array, at first I'll be declaring the tree array. Now I'll be declaring something like index, and this will be the index of the root node. And the root node will always have its index as 1. Now the left child's index will be 2 times index of the parent, and then right child's index will be 2 times the index of parent plus 1. Right. So this is the indices that we could have. Now, as I discussed with you earlier, so I'll be following divide and conquer approach. Right. This divide and conquer approach is used in algorithms like quick sort, merge sort, and so on. Now, if you remember, the first step in these type of algorithms will be to find the mid value, and partitioning the array based on the mid values, right? So I'll be trying to partition the array based on the mid value. So it will be going from start till mid, and then the second partition will be to have the partition from mid plus one, that is mid plus one index, till the end of the array. So that's what we have done over here, right? So if we take zero-based indexing, then we are partitioning it from 0 till 2, and then 3 till 5. Now the base value will be whenever we get the same indices, right? So whenever we get the array size as 1, will be going to base index. So they will be assigning the value as such. So whenever we go to the base value, or if s is equals to e, then we have come to a point that there's only one element inside the array. Then we'll be assigning the tree of index as the value that is present at the array. So let's say the array name is AR. So we'll be assigning that particular value to tree of index. Right. So now if you see, we are returning 2 from here, and then we are returning 3 from here. Now for this particular element, the answer will be nothing but it will be the sum of the children, right? So after doing this call, the current value, that is the tree of index will be tree of 2 times of index, and then plus tree of 2 times of index plus 1. So that's all. So this is how we can construct the tree array. Now let's quickly go to the IDE and try to build the tree structure for this segment tree. Now here I have my template. So now we have the elements with us, and we just need to construct the segment tree. Right? So we can do it in multiple ways, and the most recommended way is to declare it outside, that is declare it in the global space. Now, what is the recommended size for the segment tree? Now, here if you see, we just took the elements till the 13th element, right? And the value of n is nothing but it's totally 6. Right. Actually, the recommended size for implementing the segment tree is 4 times of n plus 1. This is the recommended size for constructing the tree array. And we have proof for it, which I'm not going to discuss earlier. But whenever we construct the segment tree, the recommended size to which it should be declared is 4 times of n plus 1. So let me just declare the value of the maximum size. Now let's say the maximum value that n can take is some 1000. So I'll be having 4 times of 1000 plus 1, which is nothing but 4001. Right. So let's say we construct a function over here, build tree. Now, what are the states that we could have? First important thing is the index which we are currently at. So we want something called index. And then for dividing these elements into two parts, we should need something called starting index and then ending index. Right. So int s for starting and then int e for ending. Now, we'll be passing this array that we have. Right. So instead of array, I'm having a vector over here. Right. So these will be the parameters which I'll be having for the build tree. Now we'll be having some base cases. So let's not care about the base case in the first place, but let's jump on the action step. Right. So the first step is to divide the array. So first let's take out the middle value, which will be s plus e by 2. Right. Now, with this, I'll be dividing it into two parts. So the first will be the left part. So the left segment will be having its child nodes index as two times of this index, and then the indices will be s comma mid value, and then we'll just pass in the array. Now the left or right segment tree will be having the index as two times of index plus one, and then the indices will be mid plus one, and then the ending index, and then we'll be just passing the array to it. Right. Now, these are the two partitions that we have made. Right. Now, whenever we come to the base case, now whenever these two indexes are similar to each other, then it means that we have come to a point where the array has only one element. That is this case. I'll be just going to the index of this tree. So, tree of this index, and then I'll be placing this value. And I'll be returning. Now, if you notice over here, I'm not going to return anything, right? So how to calculate the answer for intermediate steps, right? Now, what if I want to calculate the answer or the sum for the index 2? So for the index 2, the answer will be nothing but it is the sum of the indices 4 and then 5. That is its children. So for each and every parent value or for each and every index, the value will be the sum of the values that are present in its children, right? So if you go to the index 2, then we'll be getting 10 as the answer, right? Now let's try to print out this segment tree, right? So before that, let's invoke the segment tree, and the starting index will be 1 for the tree as evident from here. Now, what are the things we have? So, starting element and then starting index and ending index of the array. So, let's say we just keep them in the zero-based indexing, and we'll be passing the array or the vector. Right. Now we have built the segment tree, and now let's try to just print the values that are stored in the segment tree. So we'll be going to the maximum value, which is n, and then let's just print the value that is present in the index I. Now, as evident from here, the maximum value of n is some 4,000, and the maximum value which will be filled is 13. Right. Now, let's just print the values till 16 so that it's easy for us to visualize. Now, let's try to execute this code. So, here we're taking the input for the value of n and then the elements. Right. So, the value of n is 6, and the elements are 2, 3, 5, 7, 4, and then 5. So this is the segment tree array that we have got over here. Now let's try to verify it. So the first few values of 26, 10, 16, 5, and 5. So 26, 10, 16, 5, 5, and then 11, 5, 2, 3, and then at last it's 7, 4. So 11, 5, 2, 3, and 7 and 4. So yeah, we have got the exact array which we try to make over here. So this is how we can build the base for the segment. Now in the next video, I'll discuss about how to run queries on the segment tree and also how to do range-based updates on segment tree. So that's all about for today, guys. I really hope that you enjoyed the video and you learned something new about segment trees today. And all the videos that I make about segment trees will be added to this playlist of segment trees and range-based queries. So if you haven't subscribed to this channel, please do subscribe so that you get the latest notifications. And that's all about it. So until next time, it's me Sundar signing off from this channel. So have a good day and stay tuned for the next videos.